the clown. So, you kind of take that for what it's worth. You get to avoid a certain type of quiz. But I make up for it with, with quizzes, so, and, even that's not foolproof, but if you believe me that you're eventually going to have to know this stuff like the back of your proverbial hand. I don't know why I said proverbial. It's not really proverbial. It's literally your hand. Then you'll be in good shape. Right? Because you're going to do what it takes. Sorry, I was just cleaning that up as I was talking. You're going to do what it takes to master this, so that going forward into calculus, you're all the better off for it. All right. Now I feel the need to be like really particular. All right. So looking at number 3 on page 9, the directions, if you remember, I changed them. It was find the measure of angle theta in the figures below. All right. And the way I mentioned that we would do this is by using inverses. But before you could do that, you have to identify which trig function is most appropriate. All right. The side opposite the 90-degree angle is always your hypotenuse, poor quality H. Let me fix that. The side that's opposite the given angle, so this one over here, that would be the opposite. And the remaining side would be the adjacent. All right. So if you identify the opposite side and the hypotenuse, then the other one has to be adjacent. I always look at it like the two line segments that are in connection or connected to the reference angle, those are going to be the hypotenuse and the adjacent. All right. The one that's opposite the 90-degree angle would be the hypotenuse. You could also look at the hypotenuse as the longest side, but I don't know too many people that want to whip out a ruler just to verify that. All right. So something to keep in mind. Yeah, Jade, I got you for attendance. Thank you.
Okay, thank you. I just didn't want to speak out in front of everyone.
Oh, sorry. So I just
I just didn't want to interrupt you. It's okay.
Oh no. Okay, cool. Thank you. All right. So we know the A and the H. So here's the A, here's the H. The trig function that references the A and the H would be cosine. Cosine of theta is adjacent over hypotenuse. All right. So cosine of theta is going to be equal to 2 over 3. And to release the theta from the cosine function, we take the inverse cosine of both sides of the equation. So I say inverse cosine. Let me use red parentheses. All right, so cosine theta inside here, 2/3 inside there. Kind of overdid it with the size of my second set of parentheses here. But the reason we do this is kind of like how we take the log of both sides of an equation. Same idea. I want to release the theta. The inverse of a function cancels to the argument. All right, so in this case, the theta. So theta is going to be equal to inverse cosine of 2/3. So in our calculators, let me go back to the home screen. We don't need this. So inverse cosine, shift cosine. It says arc cosine on your calculator, but it means the same thing. 2/3. I mean, there's a reason why it's called something different, but it accomplishes the same thing. That's really the way I should have said it. All right. So hit execute or OK, and we're going to get theta to be approximately 0.841. Now that's radians. A little clue as to what type of function you're looking at, or what type of angle you're looking at, would be in the upper left-hand corner of the numworks calculator. In the orange ribbon, it says rad. So these are rads. If it were in degree mode, it would be degrees. All right. Number 4, same deal. Identify the parts of the triangle. Opposite the 90-degree angle is the hypotenuse. Opposite the reference angle is the opposite. And adjacent is the remaining side. So we have here the opposite side. Let me just highlight the 7 and then the adjacent. All right. So that means we're living with the tangent function. Tangent of theta is equal to the opposite over the adjacent. So I would say tangent of theta is equal to 7 over 1. And then we would take the inverse tangent of both sides. It's up to you. I mean, I show the work here, but you could just kind of hop to the next step if you want, right? And just say theta is equal to the inverse tangent of 7 over 1, 7. All right. That's the result. Oh, well, in case you were wondering what my statistics test looked like. I accidentally hit the wrong tab there. That's the same as saying we're taking the inverse tangent of both sides, just kind of squeezing it in over here. All right. It's up to you. You don't have to show every last step. I mean, a lot of it's calculator work anyway. So shift tan to bring up the arctan, pop in the 7, and we're going to get theta to be approximately 1.429 rad. All right. Now, the bottom question is, says find the values of the 3 trigonometric functions. That's another typo, and I meant to fix that. It's 6 trigonometric functions. All right, because we talked about this last time, where you can make 6 ratios out of any triangle when you're talking about the sides of the triangle. All right, so I want the values of 6 trig ratios for a function theta in standard position if a point with the coordinates of -3, -5 lies on its terminal side. All right, it's pretty wordy, but what that means is plot -3, -5, ballpark. Connect that point to the origin, create a reference triangle. The reference triangle always has to have a side on the x-axis. All right, so we would drop an altitude to the x-axis and create a triangle out of that, specifically a right triangle. So it would be this triangle here. All right, when they say a triangle is in standard position, that means that one of the sides is on the x-axis, and the only way that that could play itself out would be if it were the horizontal side. All right, so we know the measures here. It says coordinates -3, -5. This side is -3. This side is -5. Now the negatives in this case, the only purpose they serve is to identify the direction of the movement. So we started off at the origin and we went to the left 3 units, and then we went down 5 units. The absolute value is actually 3 and 5 for each one of those legs. But the negative sign tells us something really important, and that's the movement that gets us to that location. All right. So I'm going to use my Pythagorean theorem to figure out the missing side. The reference angle theta is going to be right here. We'll get to that in a minute. So we're saying -3 squared plus -5 squared is equal to c squared. All right. The good news is we don't really have to worry about the negatives because they're going to square away anyway. -3 squared is 9. -5 squared is 25. So I'm looking at 34 is equal to c squared, which means c, if I take the square root of both sides, c has to be equal to radical 34. So I can just kind of chuck that in over here. All right. The length of the hypotenuse is always going to be a positive measure. All right, has something to do with vectors. Whenever you're dealing with the magnitude of a line segment, it's always going to be given as a positive, and specifically the line segment referring to the vector. Right, but that more on that in future courses. For now, it's like, just believe me. Right. So I need the 6 trig ratios here: sine of theta, cosine of theta, tangent theta, cosecant theta, secant theta, and cotangent theta. All right. We're not actually solving for the angle, although we could use any one of these ratios to help us do that. I'm just identifying the ratio. So opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. I realized something. I wrote cosine again. I have no idea why. That should have been cosecant, CSC. All right, that's H over O. Secant is H over A, and cotangent is A over O. All right, so for each of these, we're just going to state the ratio. Right, it helps to identify. I mean, until you get a good amount of experience with this, helps to identify the important parts. So this is my hypotenuse, this is my adjacent side, and this is my opposite side. All right, so O over H would be -5 over rad 34. I'm going to do the reciprocals along with the functions themselves. I'm just going to smidge this over a little bit. All right, because the reciprocal function is just that. It's a reciprocal of the other functions. So sine and cosecant are reciprocals of one another. So I would make this one negative radical 34 over 5. Cosine adjacent over hypotenuse. So that's -3 over rad 34. Secant is the reciprocal of that, negative rad 34 over 3. Tangent's the only one that's, oh, tangent and cotangent, those are the only ones that are kind of clean. All right, tangent is opposite over adjacent, so 5/3. Negatives cancel away. The cotangent is the reciprocal of that, 3/5. All right. And for this, it's really just telling us all the different ways in which we can come up with the angle if we wanted to use an inverse function. All right, so the question is, how do you know when to use which function as opposed to which other function? So tangent versus cosine, things like that. By knowing these ratios, sine is equal to opposite over hypotenuse, cosecant is hypotenuse over opposite, cosine adjacent over hypotenuse, hypotenuse over adjacent for secant, opposite over adjacent for tangent, adjacent over opposite for cotangent, right? And so when you are given a triangle with a certain amount of information, let me make up a quick example here. Let's say you have a triangle that looks like this, a right triangle, and we know that this side is 2 and this side is 1, for example. All right, just keeping it simple. All right, opposite the 90-degree angle is the hypotenuse. The other side that's given is the adjacent side. All right, so I'd look at all my ratios and say, okay, well, which ones have adjacent and hypotenuse in it? So I could make a case that it's the cosine function, cosine of theta would be equal to 1 over 2. Or I could say secant theta is equal to 2 over 1. All right. The issue with using a reciprocal function is that it's not always easy to find in a calculator. All right. So I have keys that are sine, cosine, and tangent. I don't have keys for cosecant, secant, and cotangent. So my inclination would be to go for anything that's sine, cosine, or tangent. All right. And then when I go to solve for the angle, I would use the inverse function, which is also a key. Right. Now, in these numworks calculators, let's see if I remember where it is. You go into toolbox, I'll bring you to the landing page here. You go in the toolbox. There's an option for trigonometry. If you go to advanced, you'll see that they have the reciprocal function stored in here. All right. So if I wanted to do something, I'll take you to this one for a quick, for instance. If I wanted to find theta here, I would take the inverse secant of both sides. So that would be the inverse secant of secant and the inverse secant of 2. On the left, it would become theta. On the right, it would become, well, whatever the calculator says it's going to become. So I grab the arc secant function and pop in a 2. And it tells me that my answer is pi over 3. All right, so I'll show you that again real quick. So you go into your toolbox, you're on the landing page, or maybe you're where you left off, but I always like to bring it, at least for demonstration purposes, like to bring it right back to the beginning, you know, like right where the original landing page would be. Then scroll down till you find trigonometry. You don't want hyperbolic. If you hit hyperbolic, you see that it's signed, but it's got that a little extra h. All the functions have a little extra h. That's a different course. That's more Calc 2, if we even teach it in Calc 2 anymore. I got to look up the curriculum. But advanced, and you see all the different functions here. The 3 reciprocal functions and the inverse of the reciprocal functions. Now, again, I could have opted to do this with a cosine. Finding the inverse cosine of both sides does not require me to go into a special menu. That's right in the home screen. All right, so arc cosine, shift cosine of 1/2, and it spits out the same value. All right, so you can, so it comes as 2 separate ones. All right, so we're going to talk about graphing trig functions, which along the same lines as polynomial functions, rational functions, is kind of like, why do we have to do it by hand? And it's not a question of having to do it by hand. It's having a sense of what these graphs look like just by taking note of the equation. All right. So it's not so much that you'll actually have to produce trig graphs by hand. It's more so that you want to recognize them on sight, both from the equation and from the graph itself. All right. So we have to talk about things like amplitude, frequency, period, vertical translation, and phase shifting. So dive right into it. So I'm going to draw a generic sine function. All right. So a generic sine function will start off on what we call the midline. All right. So if I draw an XY axis, my sine function, this would be y equals the sine of x, would start off at the origin, increase to the maximum point, decrease back to the midline. That was shaping up to be a pretty good looking graph too, or sketch, I should say. All right. So it's going to hit its maximum at the 1/4 waypoint. It's going to hit the midline. So again, this is the midline. It's going to hit the midline at the halfway point. It's going to hit its minimum. So the minimum would be down here somewhere. It's going to hit that at the 3/4 waypoint. And then it'll be back at the midline at the end. All right. So I don't want to say it's like the 1 whole unit point, but we would say that this is the end. So it starts over here. It ends after 1 complete cycle. These are known as periodic functions. because they are infinite. So let me just show you real quick. Go into my grapher. Get rid of this function. Type in y equals sine of x. Lock it in. Go to the graph. You see, you get a whole heck of a lot more than what I just wrote here. But if we start off at 0 and work our way through, we'll work our way through one full cycle. All right. Now, you see here that one full cycle ends at 360 degrees. I actually want my calculator back in radian mode. It's going to make things easier to work with in the long run. So again, to refresh your memory on how to do that, you go on down to settings. Angle measure should be radians instead of degrees. All right, so back into my grapher, you'll see that this looks pretty hideous. So what I want to do when I create my graph is I want to make sure I have a good domain. All right. So you could do a plot restriction in here, but you could also do it in the graph. So let's say you put your equation in, you go to the graph, and you get this god-awful mess like you see here. All right. What we're going to do is go to axes. And instead of having it on auto, I'm going to change my values of x. All right. So my axes don't necessarily have to be equal. So I'm going to get rid of that. My values of x should go from not negative 491 to 491. We want to start and end our graph at 0 and 2 pi respectively. So 0 and 2 pi, it's going to convert it over to decimal form, but that's all right. I mean, if you want to just type in 6.28, you could. All right. But this is a little bit more precise, so that's why we do it with the pi notation. When I hit OK and confirm, well, actually, looking at my values of y, that's a little extreme. I'm going to change that so that it goes from, I'll go -4 to 4. You only really need to go up and down 1 unit for the standard sine function, but I'll go up 4 just so you see. All right, so that's more or less what the graph should look like. All right, the axes are not in terms of pi, they're in terms of whole numbers, but 1.5, that's about 1/4 of 2 pi. Pi over 2 is about 1.57. That 3 point whatever, that looks like some sort of estimate of pi, and so on. All right. So when I say the start and end point for an ordinary sine function, the domain is going to go from 0 to 2 pi. The range is going to go from -1 to 1. Right. But there are variations on this type of graph. Right. It's not always going to be just y equals the sine of x. It could be y equals 2 times the sine of x, or y equals the sine of 2x. All right. These values are going to impact what the graph looks like. So let me go back to expressions here. I'm going to type in y equals I said equals 2 times the sine of x. All right, so that's going to come up in that pinkish color. So orange is my original sine function. The pinkish color would be the one that's twice the sine function. So I'm going to go to graph. And you can see that this function, the one that has a 2 in front of it, is twice the height. All right, so the sine function, and we'll get to cosine in a couple of minutes, but they go hand in hand. we have y equals a times the sine of bx plus c plus d. That's the standard form, right? The a value is going to be your amplitude, specifically the absolute value of a. All right, so this is the vertical distance from the midline. Apologies, it should say maximum vertical distance. I'm going to say max vertical distance from the midline. Right, so if the a value is 2, that means that you're going to go no more than 2 units away from the midline. All right, so for an ordinary sine function, this could also be written as y equals 1 sine 1x plus 0 plus 0. So if I'm fitting that equation to this form, the a value must be a 1. So that means that the maximum would be 1 unit away from the midline. All right, and I could verify this. You know, go back to the expressions and change it to make it a 4. Go back to the graph. It's going 4 units away from that midline, the horizontal axis. All right. If I make it negative, so I'll just tuck a little negative sign in front here. It's still going to have a maximum distance away from the x-axis of 4 units, but a negative creates a reflection over the line y equals 0, so the horizontal axis. So a negative a, so if a itself is less than 0, you're going to have a reflection over the midline. All right, so I'll show you the original 4x at the same 4 sine x at the same time. Is there a duplicate option here? Would have been nice. So y equals positive 4 sine x. All right, so this is the blue. The blue one would be the 4 sine x. See that the blue and the purplish pinkish one are reflections of one another, but they're all transformed sine functions. All right, now the b value is your frequency. I'm going to make a little room here. Frequency is the number of complete cycles in the interval of 0 to 2 pi. All right, so we can repeat the cycle over and over again, but if the b value is just equal to 1, frequency of 1, then we're only going to get 1 sine wave over that interval. All right, so I'll do a quick sketch and then I'll put it into the calculator. Here's an example. Again, y equals the sine of x. Normally, it would be going from 0 to 2 pi. So here's pi over 2, pi, 3 pi over 2, and 2 pi. This would be 1 unit up, 1 unit down. The sine function starts off at the midline, increases to the maximum at the quarter-way point. That's nice. Just flat out crashed on me. It just absolutely wants to keep showing you my statistics test. All right, so it increases to the maximum at the quarter-way point, to the midline at the halfway point, to the minimum at the 3/4 way point and back to the midline at the endpoint. So this is y equals the sine of x. Poor quality. I mean, I do my best. So this is, again, y equals the sine of x. Now, if I wanted to get twice as many sine waves in the same domain, I'd have to really kind of cut every distance in half. So it'd be something like this. Right, and then repeat that again. All right, this blue curve here would be y equals the sine of 2x, because we're getting two sine functions in that same interval. All right, and again, pretty crappy drawing, but you know, hopefully it gets the idea across. I'm about to show you on the calculator anyway, but it never never hurts to get a little muscle memory with this stuff. All right, so let me go back to my expression. Expression being the word of the day. Expression, as in this word right here, expression, just without the S. Leave the last S off for savings. I'm just going to do a quick comparison. Again, expression is the word of the day. I'm going to do a comparison between y equals the sine of x and y equals the sine of 2x. It really doesn't want to accept that shift. All right. Now I think my graph settings got messed up. So here's hoping. Yeah. Let me just change my axes. I don't know why it defaults to auto. I absolutely hate that. Shouldn't do that. But it does. Let me just get rid of this. That's one thing I think the TI does a little bit better. So 0 to 2 pi. I hit shift pi instead of pi for some reason. And then, like I said, negative. Well, this actually is fine. I'll just leave this one alone. And confirm it. See, over the interval, we have two full sine waves. All right. And it's easy enough to change it so that there would be 3 complete sine waves over that interval. All right, so 3 full waves between 0 and 2 pi. All right, sometimes it's hard to see, so I tend to trace it through. So I'm on the orange one. We're going up, going back down, and then going back up. And if we go beyond the 2 pi, it'll continue the cycle. It doesn't just end the graph because we created a window. But if I bring this back to 0, see, we're starting off at 0, increase, decrease, increase, 1 full wave, increase, decrease, increase, 2 full waves, increase, decrease, increase, 3 full waves over that interval. All right, so the B value actually controls how many complete sine waves there would be in a 2 pi period. All right, in a 2 pi interval. Speaking of the word period, period is the length necessary to complete 1 full cycle. All right, and the rule for that is 2 pi divided by whatever the B value is. All right, so for example, if we had y equals the sine of 2x, and I write it using this model up here, that would be written as y equals 1 times the sine of 2x plus 0 plus d. which makes the b value equal to 2. All right, so the period is going to be 2 pi divided by whatever that b value is, in this case 2. And that's going to give you pi. Right, and if you go back to the diagram that we drew earlier, to complete one full wave of the sine function, the sine of 2x function, I should say, we had to go out pi units on the horizontal axis. All right, so this tells us how far we have to go out in order to complete one full cycle. All right, now if I need to complete 4 or 5 cycles after that, it's a different story. But at least I now know how far I have to go out to complete one full cycle. Before I get on to phase shift and vertical translation, I wanted to take a second and talk about the cosine function. So cosine is also known as the complement of sine. So I'm just going to kind of, I never give myself enough room. I'm just going to kind of tuck it off in this little area over here. Okay, that was weird. Let me just make a box. Cosine equals cosine, meaning it's the complement of sine. All right. And what that means is that if we shift the sine function pi over 2 or 90 degrees, depending on what mode you're in, you would get a cosine function. All right. So this is a pi over 2 shift of the sine function. All right. And I'll show you what that looks like. I'm just going to draw a quick sketch, and then I'll show you on the calculator. I think the calculator doesn't really handle this very well, because you don't, like, you can create a cosine function and a sine function, but you don't necessarily know where you should be looking in order to kind of make the connection. So let me just show you in the form of a sketch real quick. I just move this screen over. So I'm going to bring this in a little bit. I'm going to draw the horizontal axis, vertical axis, and I want my horizontal axis to go from -2 pi to 2 pi. Trying to keep it roughly symmetrical. All right. So if I draw a sine function, but shifted, right, but specifically pi over 2, I'm going to have to break this up. Half of -2 pi is negative pi, so that's my halfway point. -3 pi over 2, pi over 2. Then we have 0, pi over 2, pi, three pi over 2, and 2 pi. All right. Now let me show you the ordinary sine function. I'm going to start off at the origin. Max height, min height, 1 and -1 respectively. At pi over 2, we'll hit the max. Pi, we hit the midline. 3 pi over 2 minimum, and 2 pi, we're back to the midline. So it's going to look something like this. All right. And I can continue that all the way to the left, but I'm not going to just yet. I'll just kind of leave it there. Now, let's say I started off. So this is y equals sine of x. I started off my graph, instead of starting it at 0, I started it off at negative pi over 2. I don't know why I didn't put the negative sign there. I'm going to start it off here. Then I'd hit the maximum height at this location. I would be back to the midline at pi over 2. I'd be at the minimum at pi, back to the midline at 3 pi over 2, and back to the maximum at 2 pi. So it would look something like this. So I'd have my sine function, which would actually only go from negative pi over 2 to 3 pi over 2. But because I still have a little bit of domain left over, I would just start the cycle again. All right, so I would pretend that this is my starting point here, and my next stop would be to go to the maximum. So that would get me up to this location. All right. This is a shifted sine wave, but the part that's in the first and fourth quadrant, starting at 0, this part, that's the cosine function. So it's the same cycle, you're just starting at a different location. And so what most people do is they'll say, okay, well, I'm going to start my cosine at its maximum, then decrease to the midline, to the minimum, back to the midline, and then back to the maximum. Right? But essentially it's the same graph. And in fact, if I continue the trend, it becomes almost indistinguishable from a sine wave. So you're looking at something like this. And then I continue with the blue. I mean, if you follow that, it looks like, all right, they're just kind of parallel curves to one another. And that's why I was saying, if I do it in the numworks without doing the sketch first, it could be a little weird, because it's like, well, what am I looking at here? So let me just pop this in. I'll make it cosine. And I want to do graph. But like I said, I'll just do it the way I did here. I'm going to make it go from negative 2 pi to 2 pi. So negative 2 pi, 2 pi, confirm. And for the y's, I'm going to bring it a little closer. I'll make it like, I'll go negative 1.5 to 1.5. I want to go just a little bit beyond my maximum and minimum points, just so I can actually see them on the graph. And then confirm. You know, look at this. It looks like 2 parallel curves. And you get from this, okay, I guess they're kind of the similar or the same, but you never really get the active ingredient, if you will. Mm-hmm. So graphing them really isn't that terrible. If you know how to graph one of them, you essentially know how to graph the other, right? But it is possible that you could have a shifted version of a sine wave. Now, maybe that shifted sine wave is the cosine wave, but maybe it's not. Right? Maybe it's just another form of a sine wave. All right. So if we shift horizontally, that's known as a phase shift. All right. And the rule for that is negative c divided by b gives us the number of units to shift. All right. The vertical translation is a shift vertically. And that's whatever the d value is. All right. So what we do is we start off typically with a baseline function, baseline sine function, cosine function, whatever. And then from there, we decide, okay, do we have a frequency bigger than 1? If so, what does that make the period? And then am I dealing with some kind of shift? If there's a c value or a d value in your function, then you're going to have a shift. It's just a question of how far and in what direction. All right. So let me take you through. Well, the first one's kind of beating it to death. I'm going to take you through. You know what I'll do is I'll save these two for next class so that we can kind of start off with a little bit of review. I wanted to take you through something a little bit more oomphy. All right, so a little bit more stuff going on. Right. So whenever you're dealing with a trig function, the first thing you want to do is you want to match it up to the standard form. All right. So that you can pull out your A, B, and C values. So the standard form for a sine function is y is equal to a sine bx plus c plus d. All right. Now, if I rewrite this function, the 2 sine 2x, so that it's in this form, it would be 2 sine 2x, but there's nothing else. So the c and d values have to be 0. All right. So I list out my a, b, and c, or a, b, c, and d values, but really we're only going to need the a and b. 2 and 2, c is 0, d is 0. So because these two are 0, there's no shift. All right. The amplitude is going to be 2. All right. So the amplitude is 2. That corresponds to whatever the a value is. The period, which we compute by taking 2 pi and dividing it by b, that's going to be 2 pi over 2, which is just a pi. All right. So this b value here of 2 came from this. All right. So what this tells me is that it's going to go no higher than 2 units up, 2 units down, and we need to go at least pi units in order to create a full cycle. All right. Now, in terms of the domain that they give us, and it's really kind of important that we have a domain when it comes to trig functions, because they're infinite. You can go on forever. And it's not like with trig functions, you can't really put arrows on it, right? Because if I did something like this, for example, and then threw some arrows on it, I mean, that looks like a polynomial. It looks like a negative cubic function, right? There is really no way to demonstrate that the pattern continues. So what we do is we just create a graph that has a couple of cycles in it so that the reader can get a sense of what the trend is. All right. Now I want this to go out to 2 pi, and I can increment my graph in any way I want. So I'm going to let 2 boxes vertically be equal to 1 unit. You could scale it any way I want, like I said, but this is how I'm choosing to do it. Now for the horizontal, I can let any number of boxes I want be equal to pi. It's a good idea to let it be an even number, right? But and it needs to fit on the graph grid. So as long as you accomplish those 2 goals, then really anything you come up with is going to be fine, right? I'm going to let pi be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm going to let pi be equal to 8 units. I'm going to call pi 8 units to the right. I want a kind of a nice large graph so I can see all the bits and pieces. All right. So 1, 2, 3, 4, 5, 6, 7, 8. Here's 2 pi. And then 8 units the other way. Negative pi. Now, this domain is only going from negative pi to 2 pi, so I would stop there when I go to the left. I mean, if you want to, you could let 1 box equal pi units, but that's going to be a pretty compressed graph. If anything, like I said, go an even number of units for pi, but you could go 4, 2 or 4. 4, I would say, is a good minimum. Like you don't want to go anything less than 4 when you're designating the number of tick marks to let be equal to pi. All right. Now I know that I have to get 1 full sine wave in the 2 pi period. I'm sorry, in the pi period. All right. So what I do is I take my interval going from 0 to pi, and I break that into quarters, which is why I said use an even number to represent pi. So pi over 2 would be halfway. Half of pi over 2 would be pi over 4. And 3 pi over 4 would be the 3/4 way. All right. So it's a quarter, half, 3/4, and 1, but all multiplied by pi. So I need to get a height of 2, the special points again, and that goes back to this quick diagram I drew over here, where I say, this is the cycle. We start at the midline, hit the maximum at the quarter-way point, then the midline at the halfway point, 3/4 point, we're at the minimum, and then you get to the end. All right. So that's what I want to do here. I broke it up into quarters. I'm going to start off at the midline. I'm going to increase to the maximum at the quarter-way point, the midline at the halfway point, the minimum at the 3/4 point, and then back to the midline at that end point. So this is one full cycle of a sine wave. But what we have to do is what's called propagation. We have to propagate this sine wave so that it fills up the entire domain. All right. All that means is it means complete the cycle, follow the trend, complete, well, not necessarily complete the cycle, but complete the domain. Use the pattern to complete the domain. So I need to get out to 2 pi over here. It seems like every 2 units on my x-axis, I'm doing something special. All right. So if I know I'm going up to the maximum, midline, minimum, and then back to the midline, do it again. Every 2 units horizontally, that's going to happen. So maximum, midline, minimum, and then back to the midline. And then I have to backfill it. I got to follow the trend the other way, right? So if I'm going from left to right, midline, maximum, midline, minimum, then back to the midline. I like to say middle high, middle low middle. So I say, this is how a mnemonic device I use to remember it, at least early on. Middle high, so start off at the middle, go to high, then middle, low, middle. So middle high, middle low, middle low. And then for the cosine function is high, middle, low, middle, high. But that's for the next one. So high, middle, low, middle, high. It's really more about the cadence that helps me remember it. Middle, high, middle, low, middle. All right. High, middle, low, middle, high. Kind of rolls off the tongue. Right. So I'm just following the progression in the opposite direction. If I'm starting off at 0 and going to the left, I'm at the middle. I'm going to go low, back to the middle, high, and then back to the middle. Some people, I mean, to be fair, there aren't too many people that need mnemonic devices to help you remember the pattern. It's like, it's going to start here, go up, go down, and come back up. All right. It's really just a matter of fitting that to the available space based off of the amplitude in the period. All right. Now I'm going to add a little extra spice to it. First off, it's going to be a cosine function. All right. But now we have our high, middle, low, middle, high. That's going to help us. But I'm also going to incorporate a phase shift. All right. So y equals a cosine bx plus c plus d. And this is actually the first time I'm writing this, but it's the same as the sine function, same ingredients, it's just a cosine instead of a sine. All right, we identify our a, b, c, and d values by matching this up to the given function, which I'm going to write as 1 cosine 2x minus pi over 4. The d value is going to be 0 because there is no trailing constant. All right, so from here I get my a, b, and c, but no d. So my A is equal to 1. Question?
You wrote pi over 4, but I think you meant to write pi over 2.
You're absolutely right. Thank you.
You're welcome.
So the A value is 1, the B value is 2, the C value is negative pi over 2, and the D value is equal to 0. We progressed through this the same way we did for the sine function, starting off with the amplitude. That's going to be equal to 1. And again, that comes from whatever your A value is. The period is 2 pi over B. Whatever your B value is gets chucked in here. And you'll see a lot of repetition when it comes to this stuff. You know, unless somebody wants to incorporate a B value of like 17 over 4 or something like that, odds are it's going to be like 1, 2, 3, 4, you know, something in the low end of the whole numbers. Okay, so 2 pi over 2 is going to be equal to pi, which means that we have to complete the full cosine wave in between 0 and pi, but there is a phase shift. All right, the PS, the phase shift, negative C divided by whatever the B value is. All right, so here's my C. We know the B. So negative is built into the formula, and we also have a negative for the C value. And then the B value. All right, so this is going to be positive pi over 2 divided by 2. Half of pi over 2 is pi over 4. All right, so that's how far we have to shift it. When we talked about the cosine function, we shifted the sine function left pi over 2 radians. All right. Here, we're going to shift everything to the right pi over 4 radians. But I don't know where pi over 4 is because I haven't established the scale yet. So that's what we'll do here. We're going to let, and like I said before, you can kind of get sort of cute with this in terms of the domain. You can go by 4 units to equal pi, 6, 8, 10, but eventually you're going to run out of space. Whenever I have a shift, I tend to stay on the smaller side. So I'm going to let pi be equal to 4 units here. All right, I have to go out to 2 pi. I just worried that if I let pi be equal to 8, then when I shifted it over to the right, that it would go off the grid. So you're better off going a little smaller here. The amplitude is 1. So I'm just going to go up 4 units and call that 1. I mean, if you want, you could let 1 unit up be 1. But then you're going to get this little tiny graph here. If you're all right with that, and you could do it in a sort of legible way, then that's perfectly fine. I just tend to give myself a little bit more room to create the graph. All right. So the period has to be 2 pi, I'm sorry, pi. So that means in between 0 and pi, I have to have 1 full wave. So in this interval, and anytime you have a period, you break it up into quarters. All right. So if you need to, you just kind of do it off on the side. Pi times 0, pi times a quarter, pi times a half, pi times 3/4, and then pi times 1. That's if you need the values. But if you just need the location, it's like, well, there's 4 boxes to equal pi. Half of 4 is 2. That's where pi over 2 would be. That's this one. Half of pi over 2 is pi over 4. That would be this one. And between a half and a whole is 3/4, so 3 pi over 4. That would be this one. So I need a full cosine wave in this interval. So like I said, high, middle, low, middle, high. I'm going to start off at the maximum point, which would be here. And that's because the amplitude is 1. If the amplitude were 20, I would start off 20 units up. All right. Then I'm going to hit the midline at the quarter-way point, the minimum at the halfway point, midline at the three-quarter-way point, and then back to the maximum. All right. Now, this is not going to be my final answer because I have to do a phase shift. So what I do is I use a dashed curve to represent that this is not the final product. It's just kind of a baseline for me. Continue the trend till you run out of space. All right. And so what this is y equals sine of 2x. All right. I haven't taken into account the phase shift yet. All right. So I only really addressed the A and the B. So now for the phase shift, all that's telling me to do is shift every point to the right 1 unit. All right. So it's to the right because this is a positive number. All right. It's 1 unit because that's what the scale tells us. All right. So the 1 unit comes from the fact that pi over 4 is 1 unit away from 0. So pi over 4 is valued at 1 unit. So I'm going to take every single one of these points and shift them to the right 1 unit. Some of them will go out of the domain. We disregard those.
Professor, I have a question.
Yeah, what's up?
So we're dealing with cosine right now, right?
Yep.
So do we still start with y equals sine 2x, or do we?
Oh, that's a brain cramp on my part.
And my other question is this. So with sine, you shift to the left, and with cosine, you go to the right. Is there a reason?
Well, we're shifting to the right because that's what the phase shift tells us to do. All right, because that value computed out to be a positive.
Oh, okay, got it. Thank you.
No problem. All right, so now this point here, if I shifted it, it would shift out of the domain. So I don't want to do that. I want to ignore that. All right, so I'm going to create a curve here. This red curve is most of the cosine function, but I still have this little gap over here that hasn't been accounted for. All right, so I have to backfill the domain because I need to have the graph go from 0 to 2 pi. All right, and so far I have it only going from pi over 4 to 2 pi. So I would assume if I follow the trend, see how we're starting, I'll use a highlighter here. We're starting at the mid, let me make this thicker. We're starting at the midline, decreasing, increasing, decreasing, increasing. Next step would be to decrease. All right, so we would need another point over here to complete the circuit. And now we have one full, turns out it's a sine wave, right? By shifting it over pi over 4 units, if the new graph is starting off at the origin, then it must be the equivalent of a sine wave. All right. So we just graphed y equals sine of 2x minus pi over 2. As it turns out, and I keep doing it. I keep wanting to call it sine. Sorry about that. That's like the 3rd time I've made that mistake. Y equals, we just graphed what the question asked us to graph, which is the cosine function. As it turns out, this is the same as y equals the sine of 2x. It produced the same exact thing. All right, so you can have a cosine function. Cosine functions are great, but there's always an equivalent sine function out there. All right, and let me show you It's not overly complicated. It's just a matter of typing it in. If I put in the sine of 2x, and then for the second one, I put in the cosine of 2x minus pi over 2, lock it in, go to the graph, only one graph appears. Right? And that's because I'll go to the table. They're the same graph. Right? All the corresponding y values match up, regardless of how ugly the decimals are. Right? And in fact, just a kind of a word on that. If you look at these decimals, if you were to try to plot it by these decimals, it would be a nightmare. Right? Which is why we use this technique. It gives us a nice quick way of coming up with the most plottable coordinates for the function. All right. Now we're just kind of scratching the surface on this. I don't expect you to have it all mastered on day one. We need to do more practice with this. Then we have to incorporate the other types of functions in, because we talked about sine a lot. We're touching on cosine, but we have to get tangent, secant, cosecant, and cotangent into the conversation. And then there's graphs for the inverse functions. All right. Every one of the trig functions that we just talked about, they all have an inverse. So we have to account for those as well. All right. So instead of kind of hitting you over the head with too much of this, what I'm going to say is we'll just kind of leave it here for tonight, and we'll pick it up on Wednesday. All right. Let me just stop the recording.